Okay, so section B takes it just a little bit further. Um, so first of all, to look at it from a historical perspective, this mathematician became the professor of mathematics at Bologna in 1629. He did a whole bunch of stuff, but this started the idea of. Notice if we want to get a little bit more accurate, look at this particular, this is divvied up into 1, 2, 3, 4, 5, 6, 7, 8, 9. This is where we have 10 subintervals. Here we have even more. Here we have even more. So the more we divide up the subintervals, the more accurate it's going to be for your area. So Sir John Wallis comes up with the idea of using the limits, which progress into the foundation for integral calculus. This is really the basic part of calculus here. Okay, so what we end up doing, this shows kind of a little proof. Notice, remember I was talking about that width comes from the b minus a, the interval. We're going from here to here, divided by n, the number of subintervals. And then it gets into this nice, long, complicated. But if we send the number of intervals to infinity, we're going to have a formal definition of the integral. So the first thing I want you to think about is your summation is what we were doing on the calculator. That's the Greek letter sigma means sum. All right. The Roman is that elongated S. It also means sum. We're going to convert from the Greek, sending our partitions, the number from 1 to infinity. We're going to write it much more simply, and this is the integral that we've kind of been talking about. So you might want to pause the video. I would write all of this notation down. This part down here is just saying it doesn't matter what the variable on the inside is. That's just a variable, so don't worry about that. But this middle part is really important. Okay, I would also include this little picture here. And what I wrote the integral from a to b of f of x dx equals the area if everything's above the x-axis. So the integral equals the area if the area is all above the x-axis. Okay. So another little historical note, the word integration, when you're integrating, put it together into a whole. So an integral is the whole produced from integration. So Sir Isaac Newton and Leibniz, I would say those are the main guys you think of when you think of calculus. And Riemann is the guy that figured out those little Riemann sums where you divvy it up into rectangles. All right. I'm not going to spend much time on example 1. It's just using your calculator, doing that whole n is 5, 10, changing, and using the summation math 0 on your calculator. I don't want to spend much time on this because it's not going to be a huge thing. All right. Number 2, I would say would be much more important. It says using graphical evidence and the known area to find. Now remember, the integral equals the area between the curve and the x-axis if the curve is all above the x-axis. So let's graph this particular equation from 0 to 2. This is just a line, y-intercept of 1, up 2 over 1, up 2 over 1. This is just a line. We're going to shade it from 0 to 2. So that's the area we want to find. Well, what's the shape of that? That's a trapezoid. So we're going to take h divided by 2 times the quantity base 1 plus base 2. So our height is the distance between our parallel sides. This is our height, base 1, base 2. So our height is 2. Base 1 is the distance from here to here, which is 1, plus the distance from here to here, which is 5. So this is just 1 times 6 is 6. Since the area of this trapezoid is 6, the area of this integral is 6 because the area is all above the x-axis. So if you can find the area of the figure, you know the value of the integral. All right, letter B. You might not remember this, but this is half a circle. A circle of radius 1. The square root is the top half of a circle with the center at the origin. What's important here, though, we're going from where x is 0 to 1. So we are only looking at that portion of the circle. So this little quadrant here is a quarter of a circle. So the area of a circle in general is pi r squared. The entire area of this circle would be 1 squared times pi, which is just pi. Since this is a quarter of a circle, my area is pi over 4. So the integral value is also pi over 4 because that's the area above the x-axis in between the curve and the x-axis from x equals 0 to 1.